All right, so today we're going to be doing something which is generally known as the Castiglianos. Theorems. Okay, or just equations. And basically there's different version of this. So I'll just give you one, but basically at the end, they all give about the same result. All right. So the total potential energy, which really I don't like that word, but anyway, mathematically, this is the work done by conservative forces all right, can be written in terms of generalized displacements little q sub I and generalized forces q sub I. Okay, that sounds confusing, but now you're gonna see what I mean. So basically the internal potential energy is what we call the strain energy. But again, I don't like these terms, but that's what they use on textbook. So for this one, you're gonna have potential energy internal equal to U equal to 1/2 stress times strain dV. Okay, and the external will be equal to the summation of all the value of the forces times the displacements. So basically what is work is force times distance, no? So this is force times distance. This is generalized force times generalized displacement, so which is work, no? And work is the same as energy. The only thing is because the work done by the conservative forces, I'm not going to show, is generally negative. Okay? I can show you how, but this is not the point of this class. Okay, so over here, as we said before, Q sub I is the generalized force, and the little Q sub I is the generalized displacement. Okay, so the total potential energy tau equal to V internal plus V external is equal to what? Okay, so again, here I go through some stuff that really is from a class of calculus in tensors. For example, this notation here, but we're not going to cover that over here, right? So the next thing is applying the principle of minimum potential energy I mean, all this really, the idea behind all this stuff, you will start it probably if you do your master's, like in mechanical, for example, it's in a class called AE418, which is calculus of tensors, okay? And you study this stuff. All right, so now this is, how do you find the maximum or the minimum of a function? This is just mathematics. Generally, in order to find the maximum or the minimum of a function, you need to take the derivative, okay? That's what you were doing in calculus 1 when you needed to plot a curve, no? You want to know when it's going to change directions, okay? So that's basically what it is. So what you do is that you take the derivative of the total potential energy first with respect to the generalized displacement, and you know that this needs to be equal to 0, no? The slope needs to be equal to 0 to have a change in direction. Yeah, if you plot something going like this, I mean, I don't want to plot it here, but as soon as you go to the top, the curve is 0, no? It means it's going to be a change in direction, okay? So if we do this, what does that mean? That means that the partial derivative with respect to the generalized displacement or deformation of u minus u sub I, this needs to be equal to 0. Okay, I'm just going to rewrite that equation on top of the page, of the flowing page. Okay, rewriting on top the previous equation, this one here. Equal to 0. This gives you what? we do the first term minus okay, I just took the derivative, no? Now this one will disappear, so you end up with only the force. Okay, so this will yield to or you can just rewrite it as Q sub I equal to partial the strain energy divided by delta Q sub I. Okay, and this equation here is what is known as the first Castigliano's theorem. Okay, so this theorem is not really too practical, but what does it mean? What does that equation mean? That equation means that the external force, the external general force, can be evaluated by taking the partial derivative of the strain energy, okay, by the displacement, by the general displacement. You can find the force. So that's not interesting. What is interesting for us is to find what? To find the deformation, the generalized deformation, in function of the forces, no? Okay, so that will be the second Castigliano's theorem. So this time is exactly the same procedure. So this time, instead of taking the partial derivative with respect to the displacement, we're going to take it in function of what? Of the generalized force. We know this needs to be equal to 0. So we follow exactly the same procedure. But this time, the derivative is in function of the generalized force, U minus summation Q sub I. Q sub I equal to 0. So this is going to give us what? Partial U, partial Q sub I, minus the summation of the generalized displacements equal to 0, which will mean, I mean, it's exactly the same as before, exactly the same procedure. Or just Q sub I, generalized displacement, equal the partial derivative of the strain energy with respect to the general force at that location. And this is the second Castigliano's theorem. Okay, so here I have something very important to say. Okay, here you see you have the index I here and the index I over here, no? Yeah? Okay, so what does that imply is what? Is that if you want to know the deformation at one point, I, you need to have a force applied at that point. Okay, that's what it means mathematically. So do you think in your models you're always going to have a force applied at the location where you want to find the deformation? The answer is no. So in the procedure, what are you going to have to do? You're going to have to go and simulate a virtual force or a fake force and put it over there. You will calculate what will be the displacement with that fake force. And at the end, you will take that equation, your final result, and you will assume that that force is equal to 0. Does that make sense? I mean, we do an example, okay? But what is important here is that the index I indicates the force / displacement must be calculated at the same location. Okay, so enough theory. Now we're going to move to the practical part, okay? Okay, so let's say energy methods or energy methods for trusses. And again, if you go to different textbooks, you have variation of the energy method, but at the end, they're all based on the same thing, okay? Okay, so what is a truss structure? So let's say if you look at this type of old bridges with different cells, let's say it could be what? This could be a truss bridge, okay? Subjected, let's say, to a force here, Q. Okay, something important is that when you study a truss, in statics, we're doing the assumption that this member were a one force member. So they were either in tension or compression, but basically they could only carry load in the axial direction. Okay? So that's what is known as the one force member. Assumption, okay? So they can only carry loads in the axial direction. So what is the equation that we had before for the strain energy for members that are subjected to the axial loading? We had U equal to what? 1/2 integral of P squared over EA, and I think we use DS. Okay? So this is really the internal potential energy. Now, from the Castigliano theorem, we know that the external energy should be equal to what? Minus the summation of the generalized force times the generalized displacement Q sub I. Okay, so I'm not going to, you could redo the whole derivation. I mean, it's only 2 steps, but let's say, and from Castigliano's second theorem. So this one is to calculate the deformation. What will you have? The deformation at I is equal to the partial of the strain energy with respect to the general force. So this is equal to partial of the general force times the strain energy, which is 1/2 integral of P squared over EA ds. So from here, we're going to get that Q sub I. So here, just one thing, all right? Maybe there's notation. Let me add it over here. P is the force, no? So P over here will be kind of equal to Q, no? Yeah? Same force. So this will give us what? Okay, this will give us, and then the other thing to give you a hint is that the derivative of, I mean, I did it before on the derivation. Remember, the derivative of this is equal to what? 2x dx, okay? So if I take the derivative of this, you're gonna get the 1/2 is gonna disappear. Then you have 2p, so you're gonna have the 2 will disappear. Okay, I should have put the 1/2, but all right. I'll go directly to the last line. I don't wanna clutter the equation. So you do 2x, so you have 2p dp, okay? So the dp will be partial of p partial q sub I ds. Okay, the derivative of p squared gives you what? 2p dp, okay? Which is basically what you are over here, no? All right? All right. So one, let me put over here, instead of this one, maybe put derivative of p squared equal to 2p dp dq in this case, okay? All right. So now, in most cases, trusses have a constant cross section. So that means what? A is constant throughout the length of the truss. So in that case, you can rewrite the Q sub I equal to the integral. Oh, maybe I should put that. This is the length of the truss, 0 to L, P over EA partial P partial Q sub I ds. You can just rewrite it. You can leave it as on top, but if this is constant, you can just rewrite the, you know, the integral sign is like doing the summation sign. So what would be the length of each truss? So constant cross section of length L, no? Yeah. So if you do the integral and everything is constant, this should be equal to what? PL over EA, because everything will be constant, of the partial P with respect to partial Q sub I. And this is if you want 1 to n, when n is the number of trusses. Okay. So once again, if we look at the figure here, if we apply this equation, this will only show us how to calculate the displacement at this point, because remember that this Q sub I, that means that this will be the displacement at the point where the force is being applied. Okay, that's very important, guys. Okay, that's why I'm repeating it. All right, so now, yes, we go to the example. So you will see this is not complicated, but what can make it a bit complicated is that all these problems are long, all right? So I pick obviously a simple truss structure initially. So let's say you have so if you want, wait that I do the figure. So this is simply supported over here. It doesn't change anything here, but they say this is a cable, so which means the same thing. Cable. What's the difference between a cable and a truss? Is that a truss can be tension or compression. A cable can only be in tension, okay? Cannot be in compression. All right, and in this case, which is why we're gonna be able to solve the problem, let's say there's a force applied at the tip, force F equal to 100 kilonewtons. This is not a member, okay? This is just to show the geometry. And we're gonna have the points A, B, C, and D. Okay, and the dimensions, this would be 2 meters, 2 meters, and the height of the truss will also be 2 meters. So that should simplify a lot. Okay, additional data we have about this problem is that you know that the cross-sectional area of the trusses is 400 millimeters square. And you know that the cable, and I guess the trusses as well. So this is trusses, cable, and both have a modulus of elasticity of 200 gigapascals. So everything is made out of the same material. So here, we're gonna make it a little bit complicated, okay? To make sure that the point that the force needs to be applied at the location of the deformation, where we want to find the deformation. I'm asking you here to determine the vertical deformation at point C. Okay, so how do we do that? So from Castigliano's, what do we know? Q sub I, I'm not going to redo the derivation again, but I'm going to redo it very quick. We know that this should be equal to the strain energy of I at a force at point I, no? The same location. So in our case, I is equal to the location of point C, no? All right. And I'm not going to redo the derivation anymore, but this will mean basically that we had this being equal to the integral 0 to L for P over EA delta P delta Q sub I ds. And we say that if A is constant, which is the case over here, this is equal to the summation 1, 2, how many trusses we have over here? 1, 2, 3. Okay, will be PL over EA partial P partial Q sub I. So here I'm going to write it again because this is extremely important. The I and I. So what does that imply? A force must be present at the point of deformation. Okay, so in this case, I'm going to write down, since vertical deformation at point C is required or requested in this problem, comma, these different names, fake or whatever you want, but to tell the truth, I think that's because they taught it that way to me. A dummy force must be applied at point C. Okay. And this is supposed to be page 83. All right, so there we go. So we solve the problem. What is the general procedure all the time to solve the problem? The problems, first thing to do is to do a figure or a sketch. So here is not different, okay? So the first figure we need to do will be kind of similar to the one we had on the previous page. Even though I didn't do a very good job, but A, B, C, and D. So let's see, what are the forces being applied over here? We know the force F here equal to 100 kilonewtons. Now, what do we need to do? Because we need to find the deformation at point C. What do we need to apply at point C? So let's call it Q, which will be our dummy force. Okay, because we need to apply a force at point C. Now, if you have a simply supported cable over here, how many reactions are you going to have over here? You're going to have two reactions, one up, one on the side. So you're going to have, let's say, a Y and a X. And point, this one here is a cable, if you remember. So that one, what does that mean? Is that it can only be in tension, okay? So that means there's going to be one reaction in tension. I'm going to do the intention here would be dx. So now I'm just give a comment because obviously this problem is still going to be long, but it's a little bit simplified. Previously in the class note, we discussed we discussed that sometimes you have determinate problems and undetermined problems, okay? Determinate problems where that you can solve only with these static equations. And we say that the total number of unknowns in that case will be 3, okay? How many unknowns we have here? 3. So that means this is statically determined. What would happen if in this problem here, for example, if instead of having a cable, I put another truss over here? Then you will have AX, AY, DX, DY, no? The problem will be underdetermined, okay? You can still solve it, but it will be more work, no? Yeah, so just to show you here that we're doing the simplified problem for the statically determined problem. Okay, what else do we need here? The dimension, so this is 2 meters. 2 meters. And we know the height is also 2 meters. Okay, so now this becomes like a static problem. So in this equation over here that we wrote over here, what is the physical meaning of P? Remember, this is for the trusses. So the P is the axial force in each one of the trusses, no? Yeah, so that's what we need to determine. But before finding that, what do we need to determine? The values of the reactions, AX, AY, DX, DY, no? Then using the method of joint, we can solve what is the value of the loads on each one of the bars, okay? So first thing we're gonna do is to find the reactions. So this is a static problems, 100%, until we apply at the end the equation. So, all right, so let's say over here, to go a bit faster, first thing we're going to do is take moments about point A. And this must be equal to 0. So what do you have over here? Let's start by the 100 Newton force. That one will create a clockwise moment, no? So that will be the negative, so minus 100. And the arm to point A is 4 meters, okay? Now, and AX, AY do not create any moment. That's why I selected point A to eliminate the moment from these two forces, okay? So that the only unknown will be dx. That's the idea about taking the moments about point A. Now, what would be the moment created by the dummy force? That one will also create a clockwise moment, so it will be minus q, but this time the arm is 2 meters, okay? And now at the end, the reaction dx of the cable, that one will create a counterclockwise moment, so that will be positive, and the arm will be 2 meters. And this must be equal to 0. Remember that at the end of the problem, q will be equal to 0, that dummy force, okay? So we can solve dx in function of q. So this will give you over here 2dx equal to 400 plus 2q, okay? Which will just give us the x equal to 200 plus q. All right, next, we need to find ax, ay. So in order to do that, the only thing we have to do is to do summation of forces on the x equal to 0, which will give you what? Ax minus dx. I don't see anything else on the figure, equal to 0. So this will give you that ax equal to dx equals to what? 200 plus q. All right. And finally, to find a y, we do summation of forces on the y equal to 0. So this will give you summation of forces on the y, will give you ay minus q minus 100 equal to 0, which will give you a sub y equal to 100 plus q. Okay, so now that we have the reactions, we can go and find the actual forces on each one of the truss members. Okay, so the next thing is to find actual forces on truss That's it. That should be enough. Okay, so as I said before, using the method of joints, so let's see at the figure, okay? So let's start by point A, no? So in point A, how many forces are you gonna have? You're gonna have AX, AY, this force here that we can call AB, and this one AC, no? Okay, so at joint A, let's see here, joint A, this is our point A. So what do we have? We have, what is AX equal to? The way we plot it going to the right, okay? And AX we say was equal to 200 plus Q. All right? AY is plotting going up, and AY is equal to 100 plus Q. Now, the other unknowns will be equal to what? So let's plot everything in tension. So let's say, do we have a point P here? No, so let me change the name here a little bit. So let's call this one here, instead of F, let's call it P, AB. Maybe I should have plotted the other way, doesn't matter. And this one, PAC. Okay, here I don't think we need to do a very complicated math. Since everything is 2 meters, 2 meters, 2 meters, 2 meters, what should be this angle over here? And this angle over here, what should it be? Huh? This is a right angle, so it should be 45, no? Yeah? I mean, you can do the trigonometry, but I think it would be pretty fast, because what would you have? Sine of this angle would be equal to what? 2 over 2, no? Which is 1, no? Yeah? Okay. So let's just save some time. We know this will be 45. Okay, and if you want, they even say sometimes, so cosine 45 will be equal to sine 45, and that will be equal to what? Square root of 2 over 2, no? All right. So again, maybe you don't know that, but remember, like when you use the method of joints, can you use the moment equation? No, because all the points are going through the same point, no? So the only equation you can use is summation of forces on the x, summation of forces on the y. So what is the total number of unknowns you can have? Maximum of 2, no? Okay? So that's what we're going to be doing over and over. So if you do summation of forces on the x equal to 0, this will give you what? So 200 plus Q minus PAB. And then what else do we have? Don't forget the force here, PAC, times, really doesn't matter, but it should be cosine 45, no? And this should be equal to 0. Okay, so you see, I should have started from the other equation. It doesn't matter. Because how many unknowns do we have in that equation? 2, no? PAB and PAC, so we cannot really solve. So let's say now we do summation of forces on the y equal to 0. I did not pay attention. So this time, what would be the only unknown? PAC, no? So if you do on the y, what do you have? 100 plus Q minus PAC sine 45 equal to 0. So this will give you that PAC is equal to 100 plus Q divided by sine 45 which will give you PAC equal to, I hope I'm not going, maybe I'm going to do the details on the side, square root of 2 of 100 plus Q. Okay, let me see. I mean, I know you know how to do this, but let me just do it very quick. So here you have sine 45 equals square root of 2 over 2, which is equal to square root of 2 times square root of 2 over 2 square root of 2. Yeah? Which will give you what? When I go to 5, will give you 2 over 2 square root of 2, so it gives you 1 over square root of 2, no? So that's why this one moves at the top. And let's say now from the summation of forces equal equation, what do we have? We have that 200 plus Q minus PAB minus PAC cos 45 equal to 0. So this gives what? 200 plus Q minus PAB minus what we just calculated, which is equal to what? Square root of 2, 100 plus Q. Now, what is cos 45 equal to? Square root of 2 over 2. Okay, so this will give us what? Let's do one more line. This gives us 200 plus Q minus PAB. And this will give you what? Square root of 2 times square root of 2 is 2 divided by 2, 1, no? So all this stuff get canceled out. Cancel with this one. Minus the 100 plus Q equal to 0. So here the only unknown we have is PAB. So the Q's will cancel out. So you get 200 minus 100 will be 100. So basically this will be equal to 100. Okay, so that was a long time ago that you had to do that in statics, no? Okay, so we did joint A. Now you can choose to move either to C or B, but let's just go to B, okay, to follow the order. We go to joint B. How many forces are you going to have at joint B? You're going to have the force F, the P, AB that we know, no? So the unknown should be the P, BC, no? Okay? So let's go to joint B. So you have B over here. We know you have the 100 kilonewtons over here. Which color did I use on the other figure? Blue for these ones. So you were gonna have F PBC, sorry, we call them P. PBC. And now, what do you know about PAB? PAB is seeing tension, no? So when it goes to point B, what should be the direction of that force? Should be in tension, no? Because it's a one force member. Yeah? And this should be here 100. And again, as before, because of simple trigonometry, the angle over here is 45 degrees. So over here, we're lucky because we only have one unknown. So we can find PBC by either doing summation of forces on the X or summation of forces on the Y. Okay? So let's just do summation of forces on the X equal to 0. So this will give you what? 100 plus PBC cosine 45 equal to 0. So this will give you that PBC is equal to negative 100 over cos 45, or PBC would just be equal again minus 100 square root of 2, okay? Same as before. Okay, so now what you want to do? You want to go to joint C, or you just want to go to point D, to joint D? This joint D will be faster, but we can do either one you want. PBC, so the X. Okay, so it doesn't matter, we go. So Let's go to joint B, to join to point D. Okay, now let's just follow the procedure. Let's do joint C. It's going to be a lot more work, but what can we do? I don't want to do any shortcut at this point. So we go to point C. Where do I put it? Here. Maybe it's gonna be the last. So what do we have over here? We have Q, the dummy force. Here we're gonna have the PCD. Oops. Oh, sorry. Should have done it in blue. Sorry for that. PCD. Then what do we have? We have the PBC. What do we find for PBC? Oh, we have it on top. Equal to minus 100. So really the PBC, the way we plot it, was going down. So it's really going up. So it's going in compression. So that means that this one we need to plot it in compression, which would be going down again. So this will be equal to 100 square root of 2. And we have the other one, the FCD, which is equal to 200 plus Q. And that one we plot it in tension. So that means this one needs to go in tension that way. And that one should be $200 plus Q. Was it 200 plus Q or wait, PAC? No, you see, PAC is square root of 2 of 100 plus Q. Okay. All right. So over here, we only have one unknown. So we can do summation of forces on the X. And remember, the angles will be 45, no? I don't want to put too much information here, but it should be 45 and 45. So what are you going to have? PCD plus 100 square root of 2 times cos 45, which is square root of 2 over 2, plus square root of 2 of 100 plus Q times cos 45, which is square root of 2 over 2. So this will give us what? PCD plus 100, no? Because it will be square root of 2 times square root of 2 divided by 2. And the other one will be plus 100 plus Q, because you have the same thing again, no? Square root of 2 times square root of 2 divided by 2 equal to 0. So you have that PCD will be equal to what? Minus Q plus 200. Okay, so I think we finished this one. Finish this part. All right. So let's do a summary on the table. So let's say truss, and we call them what? AB, BC, AC, CD, axial force P, so let's go back to the notes. What was PAB? I have it here as 100, no? PBC minus 100 square root of 2. Go and check your notes. PAC square root of 2, 100 plus Q. And PCD minus Q plus 200. All right, let's go back. Let's go back, way back. So now, at the beginning of the problem, what do we need to do? We need to do P times L divided by EA times what? The partial of P with respect to the force at the point, no? In this case, we also use Q, which is the force we apply at point C as the dummy load, okay? So let's just put here a column. We're gonna call this one delta P, delta Q. So this one is very simple. What would be partial P with respect to Q on the first one? 0, no? The second one, 0. The third one will be square root of 2. And the last one will be minus 1. Okay, now if you want, I'm going to do a bit of, not cheating, but to go a bit fast, what would be the total value of the distance AB? Is 4 meters. What would be the total distance of BC? I can give it to you, will be 2 squared plus 2 squared, no? Square root of 2, so will be square root of 8, no? AC will be exactly the same thing. And finally, CD would be 2 meters. Okay. Okay, so now we go back to the initial page. So recalling that the vertical deformation at point C is given by what? Q sub C will be equal to 1 over 1, 2, 3, 4, 1 to 4 of the summation of P L sub I V1 over EA, which is constant, times partial P sub I partial Q. So I will be each one of the trusses. How much time we have left? Oh, we have time. So we know EA is constant. So this will give you what? 1 over EA. And now I'm going to try to change colors. For me to go to blue or green, I'm going to go to green because it's a bit finer. The blue is thick. So what is the part of the equation we need? We'll have here PAB times LAB. Yeah? Okay? Times what? Partial PAB with respect to Q. Okay? And you need to do the same thing for each one of the truss members. So the second one will be plus PBC times LBC times partial of PBC with respect to Q, plus PAC, I'm just going through the column, okay? I'm just going through each one of these values, PAC, LAC, partial of PAC, partial Q, and finally plus PCD times LCD, partial of PCD, partial Q. Okay, now if you look at the table above, what is the partial of PAB with respect to Q? You look at the table, the first two terms are actually 0, and in function of PBC, this one will also be 0, no? So we can simplify the equation. So basically, here we're going to get that QC will be equal to 1 over EA of what? Of only the last two terms. So what is PAC equal to? Is square root of 2 times 100 plus Q times the length. What was LAC is square root of 8. And now we need to multiply this by the partial P, partial Q, no? Which is square root of 2. Now we do PCD, which is equal to what? Plus PCD is equal to, oh, so negative Q plus 200 times LCD, which is 2, times partial P with respect to Q, which is negative 1. So I close here the bracket. So this gives QC. Oh, okay. I'll do one thing to go a bit faster, or we can do it at the end. setting the dummy load to 0 because we don't need it, what do we have? We have 1 over EA times what? So it will be 200 square root of 8. I don't have a calculator here, okay? So it will be square root of 2 times square root of 2 times 100, 200 no, times square root of 8. Then you have the minus sign. So it will be 200 times minus 2 will be plus 400. Okay. All right, so finally, if you remember at the beginning of the problem, we said that the Young's modulus of all the members was the same, 200 gigapascals, and that the cross-sectional area was 400 millimeters square. Which is how many meters square? Is 400. 1 meter is, so 1 millimeter is 10 to the minus 3, no? If you multiply that, what do you have? 10 to the minus 6, correct? Okay, you can do it very quick, okay? All right, so if you do the calculation, you will find that Q sub C is approximately equal to, go and check if you want, 12.07 10 to the minus 3 meters. Or you could say that Q sub C is approximately 12.1 millimeters.
Is there always a positive value?
So basically, as you can see, the deformation, to answer your question, will always be a positive value or negative value? Here comes your answer. I think you can answer yourself. You can answer the question yourself. It will have, if you were going assuming the dummy force here going up, then you will have a negative value. But because we assume the force on the same direction as the deformation, the work is positive. Remember, all this stuff is based on work, no? Yeah? So if the force is going the opposite direction at the deformation, you will get a negative value. Okay, that's a good question. So we don't have the time today, so I'm going to stop the recording. But next time, I'm going to show you how to do the finite element to check this type of problems. Okay, but you see a simple problem becomes long, no? When you need to find the deformations. So let me stop the video. Let's see if I can get the menu to show up. There you go. Stop recording.